And the next topic in tensors is the principle of general covariance. We're looking for equations that retain their form under some arbitrary transformation of the coordinates. And now that we know what a tensor is, that's given us the clue to how to construct such equations. If we want to construct an equation that's invariant under an arbitrary transformation of coordinates, all we have to do is equate one tensor to another. For example, if the tensor A lambda mu nu of x is equal to the tensor B lambda mu nu of x, then A prime lambda mu nu of x prime equals B prime lambda mu nu of x prime. So with tensors, if our equation is a tensor equation, it's guaranteed to satisfy the principle of general covariance. In particular, the vanishing of a tensor is an invariant statement. So if a tensor vanishes in one coordinate system, it vanishes in all coordinate systems. Now, we need to learn how to manipulate tensors. So the next topic is tensor algebra. And the first one is addition. So if we have some tensor A mu nu, let's say, and some tensor B mu nu, and we add them together with some arbitrary coefficients alpha plus beta, then the result, call it T mu nu, is a tensor. That's easy to verify from the definition of a tensor that we wrote down in the previous lecture. Direct products. So, and you can generalize from these examples to arbitrary tensors. But if we have a tensor A mu nu of x and a tensor B rho of x, let's say, then we get some quantity with indices T mu rho. And that's a tensor as well, if A and B are tensors. So you can multiply tensors together as a direct product and get a third tensor. Another way to get a tensor is by contraction. So this turns a tensor of rank R into one of rank R minus 2. By summing over one upper index and one lower index. For example, let's suppose we have some tensor D mu rho, then D mu rho, which is by definition delta mu D mu rho is a tensor, or it's a vector. And D mu, which is delta rho mu D mu rho, is also a vector, in general different from the other one.
Would you mind writing the indices larger?
Larger, yeah. Yes, okay.
Thank you.
And we can also do raising and lowering. Of indices. So if we have some tensor T mu rho sigma, let's say, we can multiply it by G mu nu. Sorry, I'll write them bigger. You have an upstairs mu and a downstairs mu, so that turns it into a T mu rho sigma by multiplying by the metric and summing over the repeated indices. Similarly, S mu rho sigma with an upstairs G mu nu gives me something R nu rho sigma, which is raising an index with the upstairs G. And if we do both, if we take T lambda rho sigma, and we lower the index G mu lambda, and then we raise the index G mu nu, we get back to R nu rho sigma. Now, you notice I've used different letters here, but the convention is if a tensor differs from another just by raising or lowering its index, we use the same symbol. So we can call this T nu rho sigma, on the understanding it's the tensor we started with the indices raised and lowered. Next property is symmetry. If we have some tensor with a bunch of indices, mu, nu, and it could have lower ones, perhaps. And when we look at the same tensor where the indices nu and mu are interchanged, if this is plus or minus what we started with, then we say it's symmetric under mu goes to mu, or antisymmetric. It's a minus sign. An arbitrary tensor can be decomposed for example, let's suppose we have a rank 2 tensor T mu nu. We can add the same tensor with its indices replaced, divide it by a half, and this is defined to be T mu nu with round brackets. The round brackets indicate that it's symmetric. Similarly, T with square brackets, mu nu, which is 1/2 T mu nu minus T mu nu, is antisymmetric. And the tensor we started with can be recovered by adding its symmetric piece to its antisymmetric piece. An important example of a symmetric tensor is the metric itself, which is going to play the role of the gravitational field. It will be a symmetric tensor. Interestingly enough, Einstein toyed with the idea of having an antisymmetric part to the metric. He was hoping to unify gravity and electromagnetism that way, but it didn't work. There is an antisymmetric tensor that enters into string theory, which has revived these ideas, but we won't talk about that today. So the metric, for all our purposes, will be a symmetric tensor. You can generalize this to more indices. For example, a 3-index tensor, which is totally symmetric, which means if you interchange any 2, you get back to where you started. This can be written as 1/3 factorial with 6 terms. Three of them are cyclic permutations, and 3 are anticyclic. and we divide by 3 factorial. That's the definition of the round bracket for 3 indices. And the square bracket is the same, except we add the cyclic permutations and we subtract the anticyclic ones. Now, we've already introduced the Kronecker delta, which is the unit matrix, if you like. The Kronecker delta is 1 if the indices are equal and 0 otherwise. Zeros everywhere else. Notice how it differs from the Minkowski metric. The Minkowski metric has a minus sign here. But if you multiply 2 Minkowski metrics, one up and one down, you get the Kronecker delta, which has no minus signs. So another way of saying it is it equals 1 if mu equals mu and 0 otherwise. Now we can generalize this. You can define something with 2 upstairs indices and 2 downstairs indices, which is this combination delta mu rho delta mu sigma minus the other way around, delta mu sigma delta mu rho. And we can write that in matrix form, delta mu rho delta mu sigma delta mu rho delta mu sigma. And so this combination is this minus this. That's what the square brackets mean. And this goes on. We can do it 3 times. Delta mu, mu lambda, delta rho, sigma tau is something with delta mu rho, delta mu rho, delta lambda sigma, rho, delta mu sigma, delta nu sigma, delta lambda sigma, delta mu tau, delta mu tau, delta lambda tau. And you can go on and do it 4 times if you like. But you can't do it 5 times. Anybody know why not?
Because the dimension is 4. You do it 5 times and everything.
Good, yes. If we have a tensor that's antisymmetric in all its indices, in 4 dimensions, it can have at most 4 indices. Because if we had 5 indices, it would automatically vanish. So 4 is as far as we go. So an antisymmetric tensor A mu nu, you can use this to project out the antisymmetric part of an arbitrary tensor A rho sigma. If A rho sigma is neither symmetric nor antisymmetric, this will project out its antisymmetric part. And similarly, mu lambda 1 over 6 delta rho sigma tau mu lambda A rho sigma tau. So I can do the same with 4, but mu lambda rho sigma is identically 0. Because if it's antisymmetric under interchanging any pair, if I've only got 4 dimensions, 2 of them are bound to be the same. So it's automatically 0. Any questions so far? Now there's a generalization.
Excuse me?
Yeah.
So use that formula from the delta to project out the antisymmetric part of the tensor. Then if we change the indices locations on the Kronecker delta, can we project out the symmetric parts?
I don't see how at the moment. I'll think about it. Don't see how. I mean, well, yes, you can. I've probably erased it now, but I had the example of the 3-index tensor with 6 terms. I could write each one.
What I'm missing out on is why the Kronecker delta is so tied to antisymmetry as opposed to symmetry. Maybe it's completely obvious. I'm just missing it.
The Kronecker delta is not. It's this combination with a minus sign that makes it antisymmetric. It's the product of 2 Kroneckers with a minus sign in between.
So it's the minus sign that is the mismatch.
So let's look at this. Let's look at a tensor T rho sigma, and then delta mu rho delta mu sigma plus or minus delta mu sigma delta mu rho. If it's a plus sign, we get T mu nu, don't we? If it's a minus sign, we get T mu nu. If it's a plus sign, what do we get? T mu nu plus T mu mu. Yes, so it does project out the symmetric part if I change the sign. Now, a generalization of tensors is to tensor densities. And we're going to denote tensor densities by curly letter to remind us that they're densities. And I'll tell you what it means in a moment. So suppose we have some tensor with a bunch of upper indices and a bunch of lower indices. Then if an ordinary tensor would transform like this. There'd be a dx prime mu dx rho for every upper index, and a dx sigma dx prime mu for every lower index. But a density is going to be generalized dx by dx prime Jacobian to the power w. Dx by dx prime is the Jacobian of the mapping x goes to x prime. By which I mean it's the determinant of the matrix dx mu dx prime mu. And w is called the weight. It's just some constant. So an ordinary tensor is just a special case of a tensor density with weight 0. Now, infinitesimally, dx by dx prime and the w is delta alpha beta minus epsilon alpha beta to the w, where epsilon was the infinitesimal change in the vector. This is approximately 1 minus w epsilon alpha comma alpha. So an infinitesimal change in the tensor density, that was the finite way it transforms. Infinitesimally, it transforms in the same way a tensor does, but with an extra term. That an ordinary tensor wouldn't have. And then the extra terms, the tensor terms, are, as usual, 1 for rho, one for mu, minus t mu comma rho epsilon rho. So with this definition, we can establish some rules. A, the sum of two densities each of weight W is the density of weight W. The product of two densities with weights W1 and W2 is the density of weight W1 plus W2. And contraction does not change the weight. Now, there are some useful examples that we'll come across quite frequently. First one goes by the name of Levi-Civita symbol, or it's sometimes called the alternating symbol. And it's denoted by epsilon with 4 indices, mu, nu, rho, sigma. And it's equal to 1 if mu, nu, rho, and sigma is an even permutation of the indices 0, 1, 2, 3. It's equal to -1 an odd permutation, and it's equal to 0 otherwise. Now, how do we see that it's a tensor density? Consider dx prime naught, dx mu, dx prime 1, dx rho, dx prime 2, dx, so we call that nu, rho, dx prime 3, dx sigma, times epsilon, mu, nu, rho, sigma. Actually, I've jumped one step ahead. Let's consider, do this one in a moment. Let's consider where they're arbitrary for a moment, alpha, beta, gamma, delta. What do we know about that object? Well, it's totally antisymmetric in alpha, beta, gamma, and delta, because epsilon is totally antisymmetric. Could put square brackets around that. By its definition, it changes sign under interchange of any two indices. So this object is antisymmetric in alpha, beta, gamma, delta. Now, if you think about it, there is only one up to an overall constant. There's only one tensor that has that property. And that's epsilon, alpha, beta, gamma, delta. So all we have to do is work out the constants of proportionality. And to do that, we specialize to the case 0, 1, 2, 3. And that is, by definition, dx prime dx. From which we conclude that epsilon, alpha, beta, gamma, delta is dx prime times dx prime alpha, dx rho, dx prime beta, dx sigma, dx prime gamma, mu nu rho sigma is the favorite combination. Mu nu rho sigma gamma delta. Hope you can read this. Alpha beta gamma delta on the top, mu nu rho sigma on the bottom. With this. And from the definition, that implies alpha, beta, gamma, delta is the density of weight 1. It has an almost unique property. It's, with the Kronecker delta, it's the only tensor that's invariant under a coordinate transformation. Every other tensor has different components in one coordinate system to another, but the Kronecker delta is always 1, 1, 1, 1, and epsilon is always 1, 0, or minus 1, irrespective of what coordinate system you're in. And those are the only two tensors that have that property. Now there's another example of a tensor density that's very important for the physics, and that's the determinant of the metric. The metric you can regard as a 4x4 matrix, so it has a determinant, and we define G to be the determinant of G mu nu. And because of the signature, the determinant of G will always be negative, by the way. Now that has weight 2, if you calculate its weight. How do we see that? Well, you remember by definition G prime u nu of x prime is dx rho dx prime mu G rho sigma of x dx sigma dx prime nu, and I've written it in to suggest matrix multiplication. So that says that the determinant prime of x prime is dx prime squared times g of x. So that explains why the density has weight 2. But there's another way to see it. Because you can form a determinant using the Kronecker delta, the Levi-Civita symbol, epsilon mu nu rho sigma epsilon alpha beta gamma delta G mu alpha G nu beta G rho gamma G sigma delta. That combination is just the determinant. And since epsilon had weight 1, from our rule of products, G has weight 2. In fact, I could take any tensor density I like. When I say true, I mean it's the correct equation to get det G mu nu. I use the same equation. The weight will depend on what the weight of T mu nu is, of course. But if I just want to get the weight, that's how I do it. If T had weight W, the determinant has weight 4W plus 2. Why is that? Well, again, it involves 2 epsilons and 4 T's. And according to our rule, the weight is the product. So if T has weight W, the determinant of T has weight W plus 4W plus 2. Now here's a slightly confusing issue, because different authors have different conventions. I've defined epsilon with upper indices to be a density of weight 1. But we also want to have an epsilon with lower indices. So we will define epsilon alpha beta gamma delta with lower indices to be alpha epsilon mu nu rho sigma with upper indices by lowering the index G mu alpha G mu beta G rho gamma G sigma delta. Not all authors adopt that convention. because with this convention, this equals G if mu nu rho sigma is even permutation, minus G if it's odd, and 0 otherwise. Whereas some authors prefer to define epsilon with lower indices to be 1, minus 1, and 0, the same as epsilon with upper indices. I find it more consistent that every tensor with indices down is obtained from every tensor with indices up by lowering it with G's. But beware that not everyone adheres to that convention. Any guesses as to what's the weight of epsilon with lower indices?
Same as for upper because of the product rule?
Very good. Same. You might be kidded, and none of you were, at least you didn't say so, into thinking that because that's G rather than 1, that it has weight 2. But it doesn't. It has weight 1 because this has weight 1 and these have weight 0, so this must have weight 1. Now, when we come to do physics, we want to deal with the Lagrangians, and Lagrangians involve integrating Lagrangian densities over all space-time. So that means you integrate d4x. That means the product dx0, dx1, dx2, dx3. And this is the density of weight minus 1. Because d4 x prime is dx prime dx d4x. So this has density minus 1, but there's an object with density plus 1 we can nullify it with, and that's the square root of minus the determinant of G, d4x. Has to be minus because the determinant is negative, and it has to be the square root so that we get weight 1. But that object, square root of G d4x, will crop up again and again when we come to do the physics of general relativity. Any questions? Now, since we're still on the subject of epsilons, let me give you some identities. You take epsilon, alpha, beta, gamma, delta, and you multiply it by, let's not do that. Let's take epsilon, mu, nu, rho, sigma, and multiply it by epsilon, alpha, beta, gamma, delta, with no indices contracted. You can check that that's equal to G times delta, mu, nu, rho, sigma, alpha, beta, gamma, delta. And I can get identities by contracting indices. So let me take mu, nu, rho, sigma, and alpha, beta, gamma, and trace over the sigma and the delta. This gives me G times 3. Kurecki-Delta products. Then I do it again. And I need this time to put in the 1 over 2 factorial. So I could call that 1 over 0 factorial, 1 over 1 factorial, 1 over 2 factorial. And then that's G delta mu nu alpha beta. 1 over 3 factorial. And 1 over 4 factorial. Was G. They may not be useful, seem useful at the moment, but they will be useful later on. In mathematics, antisymmetric tensors are known as differential forms, and they have a particular geometrical significance, which we may return to later on. So that was all to do with the algebra of tensors, multiplying them, adding them, contracting them. But now we want to differentiate them. Now you remember the derivative of a scalar phi prime comma mu of x prime was dx nu dx prime mu phi comma nu of x. So the derivative of a scalar is a vector. You might be tempted to think that the derivative of a vector is the tensor, but it's not. Why not? Well, let's take v prime mu of x prime is dx prime mu dx nu v mu of x. That's how a tensor transforms. So if we differentiate it, we not only get a term that we would want if it were a tensor, but we also get a term from differentiating this. So that extra term spoils the transformation rule from the tensor point of view. And we conclude that the derivative of that vector is not a tensor. But that last term should remind you of something. We came across another object that wasn't a tensor, if you remember, namely the Christoffel symbol. So we can put this together. In the right way, and we define V nu. Now, the convention we're going to adopt is a ordinary derivative is a comma mu, but we can define a semicolon mu to be the comma, should we call it lambda, plus gamma mu lambda kappa v kappa. So this is not a tensor, neither is this, but what you can show is that the combination of them is. And I want you to show that as an exercise. And this has a name. This is the derivative. This is called the covariant derivative. Now, most of the equations of physics are differential equations, so the different derivatives of vectors are going to come in all over the place. And yet, our principle of general covariance demands that our equations be tensors. Fortunately, that will be guaranteed, provided wherever we saw a derivative, we replace it by a covariant derivative. And that will ensure that our equations are tensor equations. Now, this can be generalized. Let's suppose we have a tensor T, sigma, lambda. Suppose it has more indices. Then it always starts out T, mu, lambda, ordinary derivative. And then there's a gamma term for each of the other indices. So there'll be a gamma mu, rho, nu, T, mu sigma tau to take care of the lambda index. Then there'll be a gamma sigma mu nu, sorry, lambda mu. Make sure I'm getting my indices right here, because it's easy to make a mistake. Where did kappa come from? Okay, mu nu lambda, gamma mu rho nu, gamma sigma. It should be lambda, shouldn't it? Minus gamma kappa lambda rho T mu, sigma, kappa. So the rule is the ordinary derivative and then a gamma for each of the other indices. Now, we also want a similar rule for tensor densities.
There's a mistake in the gamma that the second to last one, there's two lambdas in the parentheses.
Okay.
The third term.
Yeah, what should it be?
In the third term, there is a lambda lambda.
The lambda should be a row. Second lambda.
I can't see it from here.
The second lambda in the third term.
So what should it be?
Lambda, nu, and then row.
Lambda nu?
And
Yeah.
The other lambda should be a row.
Right. Is that okay? Now, what about a tensor density? Mu, nu. Let me just do it with two indices. And then you'll get the drift. This is equal to g to the w over 2 into g to the minus w over 2 t mu nu semicolon rho.
Actually, again, I think the row and lambda should be switched.
Here?
Yeah. Okay.
Thanks. This equals t mu nu comma rho plus gamma mu sigma rho t sigma nu minus gamma yeah, I got the minus sign. Good. Minus gamma sigma nu rho t nu sigma. So that's the same rule as a tensor, but because it's a density, there's an extra term, w gamma sigma sigma rho t mu nu. So what we've learned is we can maintain general covariance at the price of replacing ordinary differentiation by covariant differentiation. But the covariant derivative is not a unique thing. It depends on what it's acting on. The covariant derivative of a scalar, the covariant derivative of a vector, the covariant derivative of a tensor all depend on the rank and weight of the tensor or density in question.
Why did we bring up after the first equal sign over there? Why did we take out the g to the weight over 2 and write it from the g to the negative weight over 2? Why is that on the other side of the equals?
Well, you can verify from the rules of tensors that that's true, and we know this object is a tensor density of weight weight 0, and we know what its covariant derivative is. So we can use what we already know for this term in brackets to derive what we didn't know. which was the tensor density rule. Now, the covariant derivative is defined only on tensors. So gamma rho mu nu comma sigma is a well-defined object, but semicolon is not. That's not defined because the covariant derivative is defined only for tensors, and gamma isn't a tensor. So ordinary derivatives, the moral is, are different from covariant derivatives, but there are some magic combinations where it turns out you can replace the semicolons for commas and still get the right answer. What are those magic combinations? Well, semicolon mu of a scalar is the same as ordinary differentiation. That's the gradient, if you like. The curl of a vector is similarly v mu semicolon nu minus v mu semicolon mu is the same as v mu comma nu minus v mu comma mu, because the extra term involving gammas cancels out. And A mu nu let's take this to be antisymmetric. A mu nu lambda plus A lambda mu comma mu plus A mu lambda comma mu is equal A mu nu comma lambda plus A lambda mu comma mu plus A mu lambda comma mu. So if we take this magic combination, we can drop the semicolons and replace them by commas. Is that legible? Probably not. Mu nu lambda, lambda mu nu, nu lambda mu, mu mu lambda, lambda mu, nu, nu lambda mu.
There's no antisymmetric symbol in the last one.
Yeah. Another useful identity is gamma mu nu lambda with two indices contracted. That's 1 over the square root of minus g d by d lambda square root of minus g, which is the same thing as d by d lambda logarithm square root of minus g. And the covariant derivative of a vector with the indices contracted is also 1 over square root of minus g d mu square root of minus g d mu. So this is just an ordinary derivative, and yet we get a scalar if we do things the right way. Now we've defined the covariant derivative of an arbitrary tensor. What about the covariant derivative of the metric tensor itself? G mu nu semicolon lambda. Well, according to our rules, it's G mu nu comma lambda minus gamma rho lambda nu G rho nu minus gamma rho lambda nu G rho nu. But gamma itself is built out of the metric and derivatives. And if you plug in the definition of gamma that we had before, we discover that this is 0. And that's known as a metric. That is the statement that gamma is metric compatible. Now you can dream up other 3-indexed objects that transform in the same way as gamma, but which are not built out of the metric and its derivatives, for which this equation is not true. But it's true for the Christoffel symbol, and that's the important thing. Well, maybe I should pause here and ask if there are any questions. This is all very dry mathematics, if you like, but believe me, it will be useful when we come to do the physics of Einstein's equations, and the experimental tests will all rely on manipulating these tensors, so we need to get the rules sorted out. Yeah?
Since this is a little bit new to me, I just missed the part where we were taking the covariant derivative of a rank 3 tensor. How you know like which indices go where and in what order? It just is really confusing.
Did I erase it? Guess I erased it. Let me
You did the covariant derivative for like a rank 1, and that was fine. Then I got confused and went to rank 3.
So if I have a tensor with an upper index, and I take its covariant derivative, I have T mu of the ordinary derivative plus gamma mu rho nu T mu. But if it also has a lower derivative, a lower index lambda,
Yeah, that's right.
then I need a gamma t mu, call it kappa, gamma kappa lambda rho.
The first term will have a lambda downstairs.
Yes. Is everyone happy with that? Any other questions? Yes?
What is a tensor density? What's its meaning?
Covariant derivative. Physically, you mean?
Like, or physically or on mathematical space or what's the
Well, its mathematical utility is clear. It's unlike the ordinary derivative, it's a tensor. So it's something that transforms in a nice way under general coordinate transformations. That's its mathematical significance. Its physical significance, we'll have to see until we come to why these tensors are physically important. But let me give you an example. In flat space-time, energy conservation can be summarized by saying that the energy momentum tensor, about which we'll talk about later, has a vanishing divergence. In special relativity, that's energy momentum conservation. Now, in general relativity, this is not a tensor equation. To make it a tensor equation, we have to make that covariant derivative. Now, what does that mean? It means that the matter out of which T mu was built no longer conserves energy, because that would only be true if its ordinary derivative was 0. And what it's telling you is that it's the combination of the matter and its interaction with the gravitational field that's the relevant quantity to bear in mind. So the fact that you're replacing an ordinary derivative by a covariant one, in that has an obvious physical interpretation. It's not always obvious, but in that case it is. But so to see physically what's going on, we have to put this in some physical context. And we'll be doing that in a couple of lectures from now. But for the moment, we're just focusing on the math and learning how to manipulate these objects. Okay, see you tomorrow.